This video is going to discuss molecular geometry, which basically means the actual three-dimensional shape of molecules. So, before I start talking about the actual shapes, I need to define a term. So this is electron domain. An electron domain is just any potential bonding site. So what do I mean by that? Well, let's say we have some generic atom, X. Well, if we have it single bonded to something, a single bond is obviously a potential bonding site because there actually is a bond there, so that is certainly a domain. If we have a double bond, that's still only one site. So even though there's two bonds there, they're connecting the same two atoms, that's still the one single bonding site. So a double bond still only counts as one electron domain. Same for a triple bond. It's still the same site. It just means that there's basically extra electrons at that site. So that a triple bond is also one domain. And if you have a lone pair, that's why I use the word potential, because even though there isn't a bond there right now, those electrons could potentially form a bond. So that is also a domain. And one thing to keep in mind is when we are talking about these structures, we're going to be talking about the structures around the central atoms, because you could actually determine the molecular geometry around every single individual atom in a structure. So for the sake of this video, I'm just going to be focused on the central atoms in these various structures. So there's two different types of geometries. There's an electron domain geometry and there's a molecular geometry. The electron domain geometry only takes into account the number of electron domains. Molecular geometry basically breaks it down further, and for molecular geometry it matters if those domains are bonds or lone pairs. So let's talk about electron domains geometry first. So electron domain geometry, electron domain geometry if you have two electron domains, your geometry is going to be linear. And once I get into molecular geometry, I'm going to draw what each of these look like, so you'll be able to see that. But for right now, I'm just going to go through this without drawing the structures. So the electron domain geometry will be linear. 3 domains, and you get what's called trigonal, planar, 4 electron domains, and your electron domain geometry is tetrahedral. If you have 5 domains, you get trigonal, bipyramidal, and lastly, 6 domains is octahedral. And in this course, you will not see anything with more than 6 electron domains. So again, with electron domain geometry, what those domains are, bonds or lone pairs, are irrelevant. All that matters is the total number of them. For molecular geometry, we have to start to break it down more. So molecular geometry. So I'm going to set up a table for this. So I'm going to have number of electron domains, to say if they are bonds. So how many of them are bonds, how many of them are lone pairs. And then lastly, the molecular geometry. Alright. So first, if we have 2 domains, and they're both bonds, that means obviously we have no lone pairs. So, one thing to keep in mind, if every single domain is a bond, the molecular geometry is the exact same as the electron domain geometry. So this would be linear. And what that looks like, so I'm just going to use, again, X and Y as generic atoms. Just have this. Right? And one other thing to note is the bond angle. So when you say bond angle, basically we'll talk about angles between individual bonds. So the bond angle for this is 180 degrees. And I will say, actually, the bond angle is not going to be relevant. So for determining the bond angle, it's not going to be relevant whether they are bonds or lone pairs. Technically, it does make a difference, but the difference is very minor. So I'm not going to worry about it. So for the sake of this class, you can just assume that the bond angles are going to be what I tell you, regardless of if the electron domains are bonds or lone pairs. So that means that every bond angle for an electron domain geometry of linear is 180 degrees. Right. Next, if we have 3 domains and they're all bonds, of course that means it's the same as the electron domain geometry. So you have trigonal planar, which I'm just going to abbreviate a little bit right there. And what that looks like is this. Y. Oh, I'm sorry. That was off the screen. My apologies. Alright, so 3 electron domains. If they're all bonds, it looks like that trigonal planar. And the bond angle you get for that is 120 degrees. So all of them are going to be 120 degrees. So 120 degrees here. So I'm going to continue this chart down onto the next page. So let me just extend this a little bit so give myself a little more room in the last column too. Okay. So there's another option for having 3 domains. If you have 3 domains, but 2 of them are bonds, meaning one of them is a lone pair, what that is going to look like is, so now we have just 2 bonds, and one of them gets replaced with a lone pair. And of course, don't forget, these bonds could certainly be double or triple bonds. That doesn't matter. So for right now, for the sake of this, I'm just writing single bonds. So this is called bent. Now remember, it still has an electron domain geometry of trigonal planar, because it still has just 3 domains. But now its molecular geometry is bent. And again, for the sake of this class, you can assume that bond angles are still all 120 degrees. Alright, now, if we have 4 domains, and they're all bonds, once again, you just get the electron domain geometry repeated. So that's tetrahedral. Now, drawing this one, so I'm actually going to start to show 3-dimensionality in my bonds. So you see, I've got 2 normal looking bonds that are just lines. I've got this bond that's bolded, and that's called a wedge. And I've got this one made up of just lines, and that's called a dashed bond. A wedged bond means that it's kind of coming out of the page towards you, and a dashed bond means that it's going into the page away from you. So I actually have a 3D model of what tetrahedral looks like. So basically, these 2 normal lines just mean that they're in the plane of the page. So that basically here, if you think that, look at the red one and the blue one, those are basically perfectly parallel with the plane of the viewer. So those would be those 2 lines. This wedge means that it's going that way a little bit, the way that's pointing, but it's also coming out towards you. So you can see this purple is kind of coming out at you. And the dashed means that it is going that direction a bit, but it's also going away from you. And so that would be represented by this green sphere here. So this shows the three-dimensionality of the molecule. And in tetrahedral, every bond angle is 109.5 degrees. So we'll go back to here, say tetrahedral, 109.5.